Asked which of the following here is smallest. Now, this is not one of those questions where you get something like 4 root 5 and say 5 root 3 and are asked which one is biggest. In that case, you could put them both as like surds in the form root k. So 4 is root 16. Root 16 times root 5 is then root 80. Whilst over here, this is root 25 times root 3. It's root 75. Because it's square root of a bigger number here, this one is going to be larger. Can't do that here because of subtractions, but it still actually gives us a little starting point. Let's just try and write things as surds, see what happens. So I've got root 100 minus root 11 times root 9, that's root 99. Actually, they just differ by 1 here. For my next one, I've got root 64 minus root 63. Okay, there's a little pattern emerging. Root 25 minus root 24, 81. Root 81 rather, minus root 80, and root 49 minus root 48. So they're all in this kind of form. Now, actually, we can do this question very quickly now because the square root function looks like this. The gradient gets smaller as x increases. So if we're comparing the difference between two bigger square roots that differ by 1, it is going to be smaller than comparing it's the same distance here of 1 for two like smaller values of x. And so the answer is going to be A. If you had root 1,000,001 but minus root 1,000,000, the difference would be absolutely tiny. Root 1,000,000,01 minus root 1,000,000,000, even smaller again. Whereas if you look at, say, root 2 minus root 1, okay, that's actually pretty big. It's going to be like 0.4 something. So we can do it that way. I'm absolutely happy with that, but you have to know that the square root function has this kind of property. Otherwise, you get into other territory, which to be honest is going to be more complex, but let's go for it. Let's investigate root n plus 1 minus root n, because that is what all of these are in the form of. And how can we compare that? Now, when we rationalize the denominator, for example, yeah, root 3 minus root 1, we times by root 3 plus 1 over root 3 plus 1. And the reason we want to do that is because we want to get the surd out of the bottom. What we can do here is the opposite. We can actually rationalize the numerator. So what I can do is take root n plus 1 minus root n and times it by root n. I'm just going to change the sign exactly like I did over here. It's not any different really. Root n plus 1 plus root n, but then it's all over root n plus 1 plus root n. This is like really explaining in more detail why that result I used earlier was true. So now I multiply these two together to get n plus 1. Then I'll get a plus lot of this and a minus lot, so I can just ignore that. And then I'll get a minus n. And this is amazing because the n's are going to cancel. I've just got 1 over root n plus 1 plus root n. And that, remember, is this. So as n increases, we can see that root n plus 1 minus root n is going to decrease. Because as n increases, this is going to increase slowly, but it's still going to increase. And then we're doing 1 over it. And that means, yeah, we'll be doing 1 over a bigger number as n increases. The whole thing's going to get smaller. So that's a little bit of algebraic proof that what I said at the start is correct. But it's actually telling you exactly, what result you get in terms of n. So that is it. Answer is A.